But we do need better.
I always work that one out.
I want to try Chris Maroney to you.
Been using muons, but
Yeah, it's now
everything has started.
okay.
You're good?
I think so.
We're not late.
Intestinal voice.
You guys hear me on Zoom?
The Zoom guy doesn't matter. Is it turn on? I don't hear.
I see my microphone.
You really know this one. Oh, yeah, so I guess this one has to be.
I'm sorry.
You can make it louder.
You know, turtleneck.
Yeah.
Welcome to the first colloquium of the year. It's great to be hosting Dr. Karie Badgley of Fermilab. Karie received her master's degree in condensed matter and her PhD in accelerator physics from Texas A&M University, where she worked with Peter McIntyre. She's been an accelerator physicist and head of the test and instrumentation department at Fermilab for many years. She worked first as a postdoc on the G-2 experiment, and then she joined the mu-E experiment, which she currently collaborates on. And she's currently working on the mu-E solenoids. She's also responsible for magnet upgrades for the Fermilab booster, proton improvement plan, which is so critical to future neutrino experiments in the US as well. She's been an invited lecturer numerous times at the US Particle Accelerator School, which is a tremendous honor. And she also occasionally lectures at the African School of Physics. So let's please welcome Karie Badgley.
You guys hear me through this? Okay, it feels like it's getting blocked by my face. All right, well, one thing she didn't mention is that we actually met at the African School of Physics. So that's how I got connected to the University of New Mexico. All right, so today I've been asked to talk about future machines. Some people call them colliders, some people call them accelerators. I'll probably use those terms interchangeably. But because these are future projects, I'm not currently working on any of these. I will start to pick up some of the work on the muon collider, which I'll talk about, but so all of these are kind of new to me as well. So before I jump into that, I wanted to point out where Fermilab is. Everybody at Fermilab, I'm sure, thinks that everybody else knows where we are, but we're located outside of Chicago, not too far from Argonne. And if you kind of zoom in on the Google map, you can see our accelerator. You can actually see this if you've ever flown to Chicago and you look down at the right time, you can actually see this from the plane, which is pretty neat. And in addition to all the cool science that we have going on there, we also have bison. So a lot of people come to see, this is not working now. Come to see the bison. We also have this iconic Wilson Hall, which you might have seen in other presentations. So one thing I didn't realize before going to Fermilab, and went there as a graduate student to finish up my PhD, was how similar the national labs were, at least this one, to being on a college campus. So we still have colloquium, we have a cafeteria, we have facilities where people can get together. It's a user center. We actually have a bar on site, a gym, basketball courts and things like that. So it's a really nice environment, plus a beautiful, beautiful campus. So like I said, I hadn't really considered going to work at a national lab until I went there, and I was very, very happy with it, and I still am. So the Fermi accelerator complex, this is before my time. This is what it looked like when they were running the Tevatron, which just by the way is where they discovered the top quark. So we have this booster and this main injector and all these other parts that kind of fed into this Tevatron. That's the Tevatron is the big ring that you can see. But the Fermilab complex today looks a bit more like this. So we're not really using that Tevatron tunnel, but we still have this front end LINAC that feeds into the booster, which is a tiny little circle that I'm not sure I'm properly circling. Yeah, here, okay. And then that goes into this main injector recycler. This kind of little triangular section here is the muon delivery ring, which feeds the muon campus. That's where muon G-2 and mu are. And then over here, there's you could see the short baseline neutrino experiment. That's where we feed that experiment. And then over here, if you've ever dealt with the test beam, that's where the test beam lives. All right, so today I'm going to go through very basics of the accelerator anatomy. I'll talk a bit about the P5 process because that's what really led into our ideas for the future accelerators. So I'll talk about some of the proposed accelerators, and then I'll also talk about the magnets for those accelerators and how we can get there where we are with superconductors now and kind of the progress that we've made. So first for the accelerator anatomy. So again, this is very basic, but in order to have an accelerator, you need something to accelerate. That's either electrons, ions, protons, and so you have to create those in some way. So we have multiple ways of doing that. You can have something called a field emission, where you're just putting a really strong electron field to kind of pull off electrons, or something else. Thermionics, you're heating it up to where they pop off. Photo emission, so you can use the photoelectric effect to produce electrons, or an ion source where you use electron ionization or plasma. So first you have to create these particles, and then once you have these particles, our next step is going to be to accelerate them. And so we can do that with an electric field, which can be DC or AC. DC is only going to get you so high in voltage, so it's limiting. Here's a picture of our old Cockcroft Walton at Fermilab. It's beautiful, but not in use anymore. But we have other large accelerators, which are RF cavities. So here is a picture of one that's at the Paul Scher Institute in Switzerland. So this is part of their cyclotron there. So as the particles are going around, they go through this cavity multiple times. This, as they get further and further out in the cyclotron, they're still passing through it. So it's reused. And so this cavity is oscillating with some frequency so that the particles come around and hit the cavity to accelerate it again. And this thing is massive. So here's a person going in to clean the inside of that cavity, which is coated in copper. But then we also have cavities that can be stacked up in a line. So this is like a single cell cavity, and then you can pair these up so that you're getting acceleration each time the particle is going through the gap. And so this is what we use in our LINACs and in some of our circular accelerators as well. And this is just a little animation done by somebody that I work with at Fermilab, which shows the particles accelerating through there. It's kind of hard to imagine otherwise because it's a 3D process. And then, of course, the most important part of the accelerator, for me at least, is the magnets. So the magnets, once you've produced these particles, these electrons are coming off in some kind of all directions. You accelerate them, but they still need to be focused and bent and treated. So that's the job of the magnets. So you can have multiple different types of magnets. Dipoles, that's the main one used for bending. That's just creating a vertical or horizontal field. All the namings of these magnets have to do with how many poles you need to create this field, right? So dipole is just 2 poles. Quadrupole, that's just 4 poles. Sextupole is 6 poles. And the quadrupoles, those are magnets that are used for focusing. You can only focus in one direction with the quadrupoles. And then the sextupoles are used for correcting, usually for the further out particles in the beam. And then you could have, of course, all sorts of other combinations, some combined function magnets. Actually, the Fermi logo is a combination of two magnets. This is the dipole and the quadrupole. I didn't realize that until I worked there. And then, of course, we have other things like solenoids, there's kicker magnets, there's other things, but the solenoid is just like a MRI machine, right? You just have a winding with a field down the center of that magnet. And then the last part, I'm kind of embarrassed to admit, when I've talked about accelerators before, I haven't ever talked about detectors as part of the accelerator. So I decided to add it on. I know it's important, especially for a lot of people here. So I'm not going to do justice to this slide for sure, but it is a very important part. We don't just accelerate for no reason. We want to detect with those. So I put a couple of different types of detectors here. This one here is a straw tracker. This actually is a straw tracker that's used in the muon G-2 experiment. So this has two planes of straws. These are aluminized mylar straws with a wire and then gas inside. These are the crystals for the calorimeter for the muon G-2 experiment. So I met somebody earlier who was actually working on this. Yeah, so those, you might have even touched those very crystals, I don't know. Then you could have silicon detectors. Here's some scintillating detector. This is actually a plastic scintillator, which will be used for the mu-E experiment for the cosmic ray veto. And then you can have things like the Cherenkov detector, or you can have a combination. I feel really bad. I put the CMS detector up here, and this is an Atlas group. I'll have to fix that. All right, so I said we're going to talk about future accelerators, future colliders. But how do we know what accelerators we're going to need in the future? And that came out of what's called the SNOMAS to P5 process. So starting in about 2020, there was a call out to the community, the particle physics community, saying, what is it you're interested in figuring out and how do you propose to do that? And so there was a bunch of papers put forward. Started off, it was supposed to be, I think, originally SNOMAS 2021, but then I think COVID pushed it to 2020. So through this community-wide meeting, this was held in Seattle. I think there was over 1,000 people participating. They were able to put forward a set of white papers, and those went to the particle physics project prioritization panel, P5, which then put out a report that then is used to advise the DOE. So this doesn't happen in a vacuum. This process also happens in Europe, and their timescale is about 5 to 7 years, where ours is about 10 years. So this just finished at the end of 23, I believe this report came out. And you might recognize some faces here. All right, so from that, the particle accelerator physicist heard, all this motivation for this new physics. They won't go over all of this here, but we know that the standard model is not complete. We have things like dark matter and dark energy that are not accounted for, this matter-antimatter asymmetry, properties of the Higgs that we're not sure about, neutrino oscillations, we go on. But what we really heard from that was that we need higher energy and higher luminosity machines. So currently, the Large Hadron Collider at CERN is the world's highest energy particle accelerator, and we're already in the process of upgrading that luminosity for that accelerator. So that's the high luminosity LHC project. So we know we need new machines. I want to just point out really quickly that in the last P5, which happened in 2014, I was still a graduate student. I didn't take part in it, but it still has had a huge effect on things that I'm working on. So here are some things that they recommended: completing this high Lumi LHC upgrades to these detectors, collaboration on the ILC, developing this neutrino program at Fermilab. This is this LBNF collaboration, upgrading the proton accelerator there. That's the PIT2. So that's something that recently broke ground. I say recently, this is 2019. but that I'm now working on. So although I wasn't part of the P5 for this, this is something I'm involved in. There was also a number of experiments in neutrinos and dark matter. So maybe some of you guys are now working on this. And then for muons, there was a suggestion to complete the mu-to-E and muon G-2 projects. So here's our muon G-2 project. You know, we did complete it. We're still analyzing final data on that. But that was, as was mentioned, what I did my postdoc on. And then complete the mu-to-E. Sadly, this is not completed yet. We're still working on it. But this takes up a lot of my time. This is a system of superconducting solenoids. There are actually 66 superconducting solenoids. We have 52 of them in place, so we're still waiting for these front 3 and these back 11, which are still being fabricated by a vendor. But all of those hopefully come in this year, and we can start commissioning them. Another accelerator, it's not really mentioned in the P5 as a recommendation, and that's because it's outside the particle physics. It's the highest priority for the nuclear physics program. But one thing that is mentioned for this electron ion collider is that this facility can help to train future accelerator physicists. So that's something that we need to also do, which is a priority in P5, is to maintain our knowledge in accelerator physics. So this is being built at Brookhaven in the previous relativistic high hadron heavy ion collider. So that's reusing that space, and it was originally, I think, planned to start in 24, but now it's in 26. So, but this uses existing magnet and RF technology, so we're not having to push anything too crazy there. All right, so that brings us back to the current P5 recommendations. There were a lot of recommendations. You can see I've only selected ones that are more relevant to this, but that is to participate in an offshore Higgs factory. So offshore being not on US soil. So designs for the FCCEE and the ILC meet those requirements, and so we should actively engage in that. So I just wanted to talk about those two experiments. So the CERN Future Circular Collider, the EE, that's saying that they want to collide electrons and positrons. This footprint up here is supposed to show you the size of the existing LHC ring, and then this huge ring here is the proposed new ring. So we're going from something like 26 kilometer to about 100 kilometer circumference. So the pros about building this new machine is that it would be using leptons. They are almost point-like, so they have a nice clean collision. They also don't have any sub-elements, so they get all the beam energy. And the other nice thing about the FCC is that it also uses resistive magnets, so magnets that are normal conducting that we already know how to build, and achievable superconducting RF cavities. So all this technology for this, we also can already do. I think so, and then because it's a circle, it allows for these particles to pass through those elements multiple times while it's gaining energy. So we don't have to have as many elements in that ring. But the con, of course, of this is this massive tunnel. It costs a lot to dig this tunnel. So that's a big issue. And then also synchrotron radiation. So for electrons, or for all particles, you get an energy loss due to synchrotron radiation that's proportional to something like 1 over the mass squared. So, because these electrons are light, that's a bigger issue for them. I'll just point out synchrotron radiation is not always bad. There's machines that are specifically built to use the synchrotron radiation, such as the synchrotron light sources, right? So sometimes it's good, but in this case, it is not. So here's just a cross-section of the design for those proposed magnets. So this is a dipole, and you could kind of see these 2 little tubes here. That's where the electrons and positrons would travel. And then this is just normal conducting magnet. 1 Tesla is kind of the max field you get. And then for the quadrupoles, they've already, got a prototype for each of these. So like I said, the technology is already there for these particular magnets, but here you can see the 2 quadrupole paths as well. And this is just copper conductor with this iron surround. All right, so the other one mentioned was the International Linear Collider. So this is electron-positron collider as well. This one is 20 kilometers in length and has also some pros and cons. Pros being just like the FCCEE, we already can build these magnets. This is going to be using resistant and superconducting magnets, but they're both at achievable fields. And the straight path that these electrons will be taking avoids that synchrotron radiation issue. But there's a huge con here, and that's that this thing, because it's a single path, has to be very long and requires multiple elements because the particles are not traveling back through it. And so you can see the number of things that we need, something like 10,000, over 10,000 resistive magnets for this, 2,000 superconducting magnets and some, somewhere between 16,000 to 17,000 superconducting RF cavities. All right. The next recommendation, and this is, for farther out accelerators, is toward a cost-effective 10 TeV parton center of mass collider based on proton, muon, or possible wakefield technologies. So the goal here is to have a plan to build a demonstrator within the next 10 years. So essentially, by the next P5 process, you want to have a plan on how you would move forward with the demonstrator for this. All right, so one of the ideas is this proton collider, sorry, so CERN FCCHH. So here we're using protons, and if the FCCE is built, then it would benefit from using that tunnel. The issue with this particular system right now is that it requires advanced superconducting magnets. So, for a circular accelerator, you have this relationship between the magnetic field, the radius of your circular accelerator, the momentum and charge of your particles. So those are kind of fixed when we're talking about this particular setup, but we get to play with the B field and the radius. So you can kind of look at various scenarios where you're looking at different distance here, 100 kilometer, 91 kilometer, and how that affects the magnetic field and energy reach. So either way, whatever one of these you pick, they're still outside of our current superconducting magnet technology to build, reliable, cost-effective magnets. And I'll just also note that recommendation said 10 TeV parton center of mass, which is roughly equivalent to 100 TeV proton collider, right? Because protons are composite particles, and so each particle gets about 1/10 of the total energy. And then the one that's, I think, more exciting is the muon collider for several reasons. This muon collider has what was decided the best luminosity per power of the multi-TeV colliders. It has a relatively small footprint, which reduces the cost. And of course, we all like it at Fermilab because it would fit on the Fermilab site. So the muons, though, unfortunately, have a very short lifetime, 2.2 microseconds. So you have to accelerate them. And but the other good thing is that muons are about 207 times more massive than electrons. So you have that reduction in the synchrotron radiation. So this is kind of the schematic here. You have this mu injector, and then it goes into the accelerating ring, and then into a smaller colliding ring. This little gray box here for the injector, though, is actually where a lot of the issues arrive for the magnets, because inside here you have to not only produce the muons, which you do by hitting a target with protons, and that produces both pions and muons, and then there's the region for those pions to decay, and this something called this muon cooling channel. So inside that muon cooling channel, I guess I should first say, what are we doing with this cooling, right? So when we're producing these pions and muons, they're coming out with different momentum and angles. And so you want to, in order to have a very nice tight collision, you want to get those all kind of going in the same direction at the same momentum. So in order to do that, you need to cool it, which is just reducing its momentum spread in the horizontal and longitudinal direction. So the longitudinal direction is taken care of by passing these muons through some kind of absorber. It's actually a wedge-shaped absorber. So that kind of reduces the momentum in all directions, and then you pass it through an RF cavity to bring back some of that momentum, but only in the longitudinal direction. Then those absorbers also, I said, are wedge-shaped, and that's designed to pass the higher momentum muons through that thicker part of the wedge and the lower through the lower part of the wedge to try to also reduce the momentum spread in the longitudinal direction. So there are a large variety of challenging magnets within the muon collider, but I think the two most challenging are this 20 Tesla capture solenoid, which we need at the target where these ions and muons are being produced. And that needs to have a huge 150 millimeter bore. And then as you go on in the cooling channel, you're using these solenoids also for focusing. So at the very end, you're getting up to a 40 to 60 Tesla in the final stages with the 50 millimeter bore. So those are kind of some huge challenges for this muon collider. There are other challenges that I'm not pointing out for any of these systems. And that has to do with, as soon as we're increasing energy and increasing, these rates, we're getting larger heat loads, larger radiation damage to all materials, the detectors, magnets, superconducting RF. In the muon collider, we're trying to operate superconducting magnets around RF cavities. So we're having to use resistive cavities there because the superconducting cavities don't like magnetic fields. So there's a lot of challenges. All right, I'll mention this other one just because it's fun. And it was proposed by my PhD advisor. So there were a lot of accelerator proposals put forth to P5, something like 32 or so that they were looking at. Too many to cover here, but one of them was this collider in the sea. So the proposal is to put in, this is the Gulf of Mexico, a huge kind of underwater tunnel. And the nice thing about this is that that huge tunnel allows you to use the low magnetic fields that we can, low field magnets that we can already produce. And of course, it eliminates tunneling costs. You still have to make this thing and make it to where it can stay underwater, but the tunneling costs are huge. And another thought on this was that you could use the SCC tunnel, finish that up, and use that as an injector into this. So just thought it's a fun thing, and just to remind yourself to continue to think outside the box, right? All right, so the timeline for some of these, if we look at what's planned at CERN, so we have run 3 going on right now. Then the high LUMI LHC upgrades happening, so that would then turn on. There's also kind of a planned deadline to complete this FCC feasibility study somewhere in 2025. Then if that all goes well, FCC EE would be here, and then FCC HH somewhere out here. At Fermilab, we're working on PIP2 into this LBNF dune. And then after that, we would maybe have a chance to work toward this PIN-TeV muon collider. That of course assumes that we come up with a nice muon collider demonstrator design in time for the next P5, and that it gets funded at the next P5, and we could start fabrication of that. I should point out that CERN also has interest in making the muon collider there, so there's some potential tension that maybe Maybe if this doesn't go through, they would want to pursue the muon collider, or if ILC goes through, maybe this doesn't, I don't know. And then yes, also the ILC. So if this gets approved soon, would be operational sometime in the 2040s. So I point this out because for myself, I don't know when I'm going to retire, but let's say it's sometime over here. But for you guys, the students at least, you're going to be finishing your PhD, working on a postdoc sometime into the next P5 process. Make sure your voice is heard, you have input, because that'll be what you're next working on for the rest of your career, potentially, if you're affected by any of these projects. So just wanted to put that up there. I don't know about this guy. If any of us will see that. All right. So just a quick summary. We know we have huge magnet needs for these future colliders, high field dipoles, large high field solenoids, and we need to operate in things like a high radiation environment. And another thing I didn't quite point out is as soon as you start trying to make larger and larger fields, the magnets start kind of pushing on themselves outward to try to repel that, right? So they get higher and higher stresses. So you get to the point where you're making these really large structures to try to just contain that magnetic field and forces. And so that also increases the cost and size of these. Okay, so what can we do about this? So right now, the conductor landscape for accelerators is that we have resistive and normal conducting conductors, normal conducting magnets. These are typically copper, but they can only really produce magnetic fields up to maybe 2 Tesla. So anything over that, you're going to have to look at superconducting. And in the superconducting, we have 2 different types. We have this low temperature superconductor. Those are ones that require liquid helium to stay superconducting. And then we have these high temperature superconductors, which can use maybe liquid nitrogen or maybe gaseous helium to remain superconducting. So we have these. So let's look at the properties of some of those. Oh, before I get to that, I just want to mention kind of how we make these superconductors, because it comes up later. So one way we do this is to take what's called a monofilament rod. So you take the material you're interested in, whether that's niobium titanium or niobium 310, and you put it in some matrix. So, and many of these examples, that's just a copper tube. You have a copper matrix. Then you stack a bunch of those filaments together, and you create what's called a billet, and then you start extruding that billet out until you get these fine, long filaments. And you want to do that because the superconductor has properties that if they're too big in diameter, they can be unstable to external magnetic fields. Talk a bit more about later. Once you have those fine filaments, that's not really what you want to use to wind your magnet, because if you just make one long wind of a filament and something goes wrong with that filament, your magnet's dead. So instead, you want to take multiple filament paths, put them all together in case one degrades. You can kind of current share with the other wires. So the most common way we do that is this thing called a Rutherford cable. So you take those filaments, you twist them around, a device twists them around this mandrel and then squishes them into this rectangular shape. And so this wire is here, and then it gets transposed to the other side, gets transposed to the other side. So this is important for a lot of reasons. It helps, like I said, with the reduction of external magnetic fields, causing issues on this conductor. But you can kind of see the cross section of it there. If this looks familiar, or if you're having trouble visualizing this, it looks exactly like a Twizzler. So if you've ever taken a Twizzler and looked at it, it wraps around the exact same way. I have no idea why Twizzler did that. All right, no talk on superconductivity would be complete if I didn't point out the discovery of superconductivity. So that happened by Kamerlingh Owens in 1908. He was trying to, he had liquefied helium, and he was trying to do something with mercury, conductivity or whatever of mercury. And he found that at a certain temperature, the resistance of this just dropped to 0. And then shortly after, he won the Nobel Prize. So this temperature where this thing, dropped to 0 resistance is what we call the critical temperature. So it's one of the important things for a superconductor. In order for it to stay superconducting, you need to operate below that critical temperature. But unfortunately, that's not the only thing to keep this superconducting. You also have to be below a certain external magnetic field. That's called the critical field. And it can only have, so much current density flowing through it. So these three properties, this temperature, external field, and current density, create what we call this critical surface. So you actually have to stay below this critical surface in order to stay superconducting, and above it, you're normal conducting. One other issue with superconductors is that if you are superconducting and then suddenly you're not, you have this huge amount of current that the superconductor is not able to carry. So it has to go somewhere. So that's part of the reason why you put that superconductor in something like a copper matrix. That helps distribute the current out. It's still not quite enough. You have to dissipate that current quickly or it'll destroy your superconductor, but it helps. So one of our units of measure for a superconductor is this engineering current density. So that's how much current one little strand can carry divided by the area of the strand. And that's because the strand is made up of not just that superconductor, but the copper or whatever other matrix you're using. So if you have a tiny little superconductor, but your strand around it is massive, then you're not going to make a very good magnet with that. You'd have a very low engineering current density. All right, and that brings us to our favorite so far, superconductor, which is niobium titanium. So this has been used in all superconducting accelerator magnets to date. Okay, this is our workhorse superconductor. We first started using this as a large scale when we were making the magnets for the Tevatron, and that large scale up in our production actually allowed for things like MRIs, because then they had access to cheap superconducting materials. It's ductile, meaning you fabricate this, and then you could take this and just wind it around like you would almost like a copper wire. So you can bend it. It's happy with that. You can make small radius bends. It doesn't mind that. And so that's what we call react then wind. So you make it somewhere and then you wind your magnet. And so here's just a cross section of some Rutherford cables that are making up some cosine magnet probably. And then this is the Rutherford cable used in the mu to E transport solenoids. This one, we have copper around the individual pieces that make up the Rutherford cable, but then we extruded it into this aluminum stabilizer for thermal properties unrelated to superconducting, but I mean, just for mu to E, this particular stuff is in the high radiation environment, so the aluminum helps with that as well. Not important for that. Okay, so this is a plot that's maintained by the National High Magnetic Field Lab. So here we're looking at current density and applied magnetic fields. This is the external magnetic field that this superconductor can operate in. And so for niobium titanium, you can see we're kind of in this, up to 10, maybe 15 Tesla range, mostly 10. But for these new machines, we want to be somewhere over here, right? We have large external fields that are going to be applied to these conductors, and we want really high current densities. So niobium titanium is not going to get us to the next generation of accelerators. Another conductor that's kind of come up more recently is this magnesium diboride. This one's actually not very useful for superconductors, but I just wanted to put it in here for completeness. This one is not quite as flexible as the niobium titanium, but it can still be produced in this react and then wind method. It does have a higher critical temperature, so that's 39 Kelvin. So you can potentially use helium vapor or conduction and cooling instead of liquid helium to cool this magnet, which is nice because you can save a lot then in your cryogenic costs. But this is really now being looked at more for non-high field magnet applications such as motors, generators, MRI, transmission lines, things like that. And so you can kind of see, here's where our magnesium diboride gets us. So not very much in the current density, but it's happier in slightly larger fields. So we have to keep looking. The next conductor is this niobium 310. So this is also a low temperature superconductor. This one is problematic for several reasons. One is that you can't produce this wire and then wind it around your magnet, because once it becomes superconducting, it's almost like a ceramic. It'll just kind of crack and it's very brittle. So you have to take this, these extruded wires in this Rutherford cable and wind it around your mandrel of your magnet and form it in the final shape that you want. And then you have to bake it. And the baking process is up to 650 to 700 C, which means the mandrel that you're winding it on also has to withstand that high temperature. The other issue is that it slightly expands when you bake it, so you have to plan that out in your winding and fabrication process. And it's very strain sensitive. So if it tries to crack or move a little bit, you're going to get degradation in your total current density. And this was actually discovered before niobium titanium, but because of all of these issues, it's taken, this was discovered in the 50s, it's taken all this time to really get it to where we can put it in a superconducting magnet from accelerator. And I will say that we have actually now built 2 magnets that are these magnets for the high Lumi upgrade for LHC. So inside this cryostat, there's 2 quadruple magnets made out of niobium 310. So we've shipped 2 of these now from Fermilab over to CERN. There's 10 in total that we're shipping. So this will be the very first ever niobium 310 magnet in an accelerator. So it's similar process. We make Rutherford cable. You could see kind of some of this deformation when you produce this Rutherford cable. You get some deformation here, which causes some strain on that conductor and can reduce your current density. But so there's been a lot of research in these many years to get this to where we can actually use it. So that gets us kind of over here, which is better because yes, we can produce these magnets that can operate in a higher field, but we still don't have the current densities we want in those higher fields. So we keep going. Next is bismuth 2212. This 2212 in my breakdown of the conductors I had on the other page, it showed you what that meant. Sorry, I should have pointed that out. Then it's the different ratios of the other components of this superconductor. So this is produced in the same way. You put the powder inside some tube. That tube is used to keep the powder from interacting with something else. Unfortunately, bismuth 2212 doesn't really like copper, so you have to use silver. So now you're putting this powder in a silver matrix. And this one also requires that you wind and then react, but it actually needs to be at an even higher temperature. So this makes the materials that you want to wind it on even harder and the insulation you want to use even more difficult. And when they were first experimenting with this, they kept finding voids in these superconducting wires. They would wind and react and they would have some issues. They'd look and there'd just be like a missing piece essentially in the middle of the superconducting powder. And so one way around that was to then bake this in an overpressure of oxygen and argon. So now you have a really hot magnet in an oxygen environment at high pressure. That just sounds terrifying. But it does have a higher critical temperature and it can live in a larger external field. So the other nice thing about this is it's the only high temperature superconductor. So now we're getting into higher temperatures that allows you to still put it in this Rutherford cable form, which we like because we're familiar with winding those, and it allows us to get a nice precise location of the currents that gives us then a nice magnetic field. But this one is even more sensitive to strain than the previous one, the niobium 310. But you can see we're starting to get now over in this region. So this is actual data. This is projected data. So we don't really know if that's true. If we had looked at the at the niobium 10 right here, we might have thought that that was going to go out too, but so who knows, this could fall off. But right now it's promising as a superconductor for high fields. All right, and that leads us to the last one I'll talk about, which are these rare earth barium copper oxides. So you have barium copper oxide, and then you put some rare earth metal here. So yttrium is one that we use a lot. So YBCO, you'll probably hear that term. And these are fabricated in a completely different way. So these you have to take some substrate and deposit this YBCO on top of it. Just give some copper stabilizer, some substrate, you deposit on it. Maybe there's a silver overlayer because it also reacts with copper, and then you have copper on top of that. So you make these really thin tapes, which are not ideal for winding superconducting magnets. The other thing is that it's difficult to scale this, right? You're doing this, evaporation essentially of this material on these little wires, so it's hard to scale up. So it's very expensive right now, but luckily the fusion community is interested in this material, so they're helping with the research and helping driving the cost down. So it is a higher temperature superconductor, and so that allows us to think about trying to cool this with liquid nitrogen or with the conductive cooling instead of using liquid helium. So there's several forms of this rare Rebco cable. One keeps the cable in this kind of flat arrangement, but makes it look more like a Rutherford cable. So you take this material and you kind of form it in a shape that you can kind of, I don't know, like braid it together essentially. So make these interchangeable layers. But of course, again, this is hard to scale. And so that's this Rebel cable here. And they actually used this idea back in 1914 on copper wires for AC machines before Rutherford did his magnet design in 72. Another thing you could do with these thin little films or thin little tapes, is wrap it around a core in the middle. So this is called a conductor on round core or cork cable. So you take these thin tapes and you kind of spiral wound them in opposite directions, alternating around this inner mandrel here. So you get these layers of superconductor around this wire, which is nice because now we're getting back to something that's round and we're a bit more familiar with for using this for magnets. And so here's an example of that cork cable. This is the first layer of something that's called a canted cosine theta dipole magnet. And so this magnet will actually have two layers. It looks kind of like a solenoid, but slanted, which produces a magnetic field pointing both axially and down. And then you wind the other one, so it's pointing axially and down the other way. So the axial parts cancel out and you just get a net downward, which is the dipole field you want going through the middle. So that's being done at Berkeley. And then another proposal with these thin tapes is to take something like this copper. I don't know if you can kind of see this. There's a copper inner piece that has square channels milled out of it that are twisted around this copper inner piece. And the tapes are then laid inside that copper channel. So you have a series of tapes twisting around one, 4 tapes twisting around the other. And these are all the layers of tapes that go inside that little channel. And then they take and pull what's called vacuum epoxy impregnation. They pull the solder into that channel to help stabilize those layers of tape and also help cool them, right? So they're cooled with this inner cooling channel so that conduction cools up to those tapes through that copper and solder. So this is called the Viper cable. This is being made with a combination of somebody at MIT and Commonwealth Fusion, which is a fusion company nearby. And so this is looking pretty promising too, because you have this well-stabilized tapes, which is nice. And you have this round conductor, which is also nice because we can use that for superconducting magnets. And now if we look at where the Rebco is getting us, it's really leading us into this region that we need to be in for these higher field magnets. So this is exciting. This is where we want to be. But like I said, there's still a lot of research that needs to be done and some engineering that needs to make this so we can scale this up and reduce the cost. Okay, so slight aside now on the way we've been building magnets for accelerators. So most of our magnets, we need that dipole to bend the beam in a circle. So most of our magnets have been this cosine theta distribution. So what that means is the conductor follows kind of a cosine, right? Cosine is the maximum here and falls off. So all of these magnets are using this cosine theta design. So this is the Tevatron, you have these two small layers. As you start getting up to LHC and beyond, the number of layers that you need to increase the field in the middle starts to go up, right? So 2 is manageable, but as soon as you start putting these other layers out here, you're increasing the field on these inner layers, which causes them extra stress. And these inner layers are all trying to kind of push out, so that causes mechanical stress on these outer layers. Okay, so that you're fighting yourself to try to create a bigger field in here because you're putting too much field on these conductors and too much strain on the rest, right? So you're really not getting where you need. So so that leads me to this plot on the strain. Sorry. So I mentioned that niobium titanium was great because it was very flexible and we can wind it around. So this kind of gray plot here shows us the applied strain and then the current as a function of that applied strain. Right? So we're not degrading the current much when we start moving that niobium titanium wire around. That niobium 310 and those other 2212, they all really do not like to be bent, so they're kind of stuck over here. But these cork cables are looking promising because they're also not showing much degradation when we strain those. So that's promising. So one way we can try to overcome that issue of adding multiple layers and causing additional strain or reaching too high of a field on the inner layers is to make some hybrid magnets. And so this proposal is to take the inner layers and make those out of maybe high temperature superconductor that allows for a higher external field. And then the outer conductor is these more traditional low temperature superconductors, which are just adding to the field inside. That's the hybrid magnet. And right now our record for our field inside of, this is actually a solenoid, is held by the National High Field Magnetic Lab. And that's 32 Tesla. And so this is a combination of low temperature superconductor and Rebco. So these kind of layers of Rebco in the middle where the strain and field is highest, and then the niobium 310 on the outside, and then niobium titanium on the outside of that. And the National High Field Magnetic Lab wants to create these large solenoids with large fields because in order to develop the cable we need for these higher field magnets, we need to test these cables in a large external field. So we're kind of chasing ourselves, right? We need a large field to see if our field will work on our conductor, right? So, so we try to make these facilities where we can put a sample conductor in there, run current through it, and see if this large external field is going to cause it to quench. I mentioned, oh goodness, I'm running out of time, sorry. I'll try to talk faster. I mentioned fusion is helping us bring down the cost of conductors. So Commonwealth Fusion is trying to produce this spark, which is the smallest possible, affordable, reliable, oh goodness, compact reactor. So they're trying to use these high magnetic fields to contain a plasma to do fusion. And because they need those high fields, here they're producing a coil that's 20 Tesla. They need these high temperature superconductors. And so they're using a couple of things. They're using cork. So I think this one was wound with cork. So this is a huge magnet, right? That's this magnet here, this guy can stand in. And that's, like I said, in conjunction with the MIT Plasma Fusion Lab. There's also ITER, right? So this is another fusion experiment. This conductor is a little bit different. It is using Nibium 310, so that's would be the next kind of machine using Nibium 310. But this arrangement is what's called cable and conduit. So here you have a cooling channel and your conductor around that. So it's right next to that cooling channel. And then you have this outer jacket to kind of stabilize it. So they're making these huge magnets from that. Not these huge D magnets. This is actually the material for this inner superconducting coil. This ITER facility, if you're not familiar with this is massive. This is multiple stories, right? This is a magnet that is multiple stories tall. So, and the central solenoid itself is not huge, but the other surrounding magnets are. So, a big impressive facility. So that would be good if we can get that up and running with the Nibium 310. At Fermilab, in my building, we are building right now a high field vertical magnet test facility. That name happened before I took over the department. So high field VMTF. So this is a giant pit we've made in the ground with some shielding around it. And Berkeley is producing a 15 Tesla dipole magnet, which will go in to that cryostat. And that'll allow us to run samples, put a sample in there, put it in an external field, run it up to high currents. So this is actually partially paid for by high energy physics, but also fusion energy science, because the fusion people want to come to our facility and test wires in there. So that'll be pretty exciting. So that's in construction now. And then we're also looking at, as we try to participate in the muon collider, we're going to need to test these large superconducting solenoids somewhere. And so we're looking at reusing one of our cryostats and putting this together as a solenoid test facility, a high field solenoid test facility. This cryostat was originally actually used for the mice, the muon ionization cooling experiment. And then we used it for testing our transport solenoids from U to E. So this, the scale of this is, there's a guy standing here. I don't know if you can kind of see that. So this is huge. I mean, this is a very large cryostat. I joked that after we were done, I would like to take it and fill it with water and some heater tape and make a hot tub, but we didn't do that. So instead we're going to reuse it for science. But so that's our plan there. And I'll also say that the US has a magnet development program. So this program was put together in 2016 to try to steer our magnet development research, as we knew we were needing these higher magnets for things like high lumi. And then recently we've had to update that roadmap. So we added this whole new section, which is the high field solenoid section. So that's kind of embedded now in our magnet plan and our magnet research in the US. All right, so with that, I'll conclude. Almost on time. So I'll just say it's an exciting time, a very challenging time for accelerator R&D, especially for the younger generations. Superconducting technology is progressing, but we still have a way to go. And luckily, we are being helped slightly by the fusion community. And as I tried to point out, but maybe didn't emphasize enough, it's not just the magnets that need R&D, but the targets, the RF cavities, the detectors, the cryogenic systems, and we need significant R&D in all of these areas to achieve these higher energies and rates. And another thing I didn't point out was this is also not all free, right? So in addition to all of this, we need to consider cost and schedule, size, energy efficiency, environmental impact of all these conductors and accelerators as well. So feel free to reach out to me if you have any questions about accelerators or Fermilab. If I can't answer them, I'll at least put you in touch with somebody who can.
Take questions freely.
I will freely take questions. I already got a lot of good questions over lunch with the students. Yes.
When you're part of certain magnetic field versus current,
Yes.
are there bounds placed by superconducting physics on this, or are these all engineering challenges? I know there's a lot we don't really know about. Like, is there some exclusion zone that you can say we'll never be able to achieve
Not that we know of yet. I mean, we just keep trying to push higher and higher. I know that there's some people trying to use AI to try to predict what other materials would be superconducting. So there's kind of a push in that direction. So I think we're still just exploring this whole space. Yes.
So you get, you say getting help from, the fusion community. Is any other commercial applications that are helping things, levitating trains or any of that stuff?
Yeah, so as soon as any of this becomes slightly less expensive, I think the other companies would come in, but they're not there for the initial R&D. We had this issue actually with solenoids for large detectors, right? For the mu-to-E experiment, we were getting low on our conductor that we had, and we wanted to procure some more. There's no company right now in the world where we can buy more niobium titanium extruded in aluminum conductor. That the company just doesn't exist anymore. And it's not really viable for companies to continue doing that research when we come along every 10 to 15 years and say we need another big solenoid, right? So it's these other companies don't really come in until I think it's a bit cheaper. So.
For the 20 Tesla, 150 millimeter bore magnet, what kind of current density did you need? Like, is that point up there already good enough or?
I'm not exactly sure the current density on that one. I'd have to look at. I mean, you could do several different designs. That's the other thing, right? So you could have a hybrid design in which you would need a higher current density on the middle and fewer on the outside. So that particular magnet is still part of our research that needs to be done. When we say, hey, this is our plan for the muon demonstrator, we need to still develop what that magnet actually looks like. So I can't say what the cross section and current needed yet are. Yes.
I just have to go back to that wonderful proposal that your advisor, you said.
Yes. Sea lab.
Gulf of Mexico forever. So in the Gulf of Mexico, what did you say the ejector was gonna be?
The superconducting super collider.
Oh, okay, that
Yeah.
didn't work on your slide, it was SCC, but it's.
Oh, SSC, sorry. Yes,
That's what I
typo.
thought.
Yeah.
How seriously is that supposed to be? I imagine the engineering challenges are ridiculous.
Yeah, so when he first, I was actually still in his group when he first thought of this. And I said to him, you know, Peter, you've yelled at us all the time, all plumbing leaks. So why are you going to put this in the water? And he was like, and he came back the next day and he said, all the accelerators now are already below sea level, essentially. You know, they're already below the water level, not sea level, but water level, right? So you have, you know, Oak Ridge has, when you're going down into their accelerator, if you've been there, on the stairs, there's the water line is actually drawn out, and you know when you're going below the water level. But as was pointed out, it's different pressures. So I don't know how seriously it was taken. I wasn't on the P5. Maybe somebody who was could answer that. No. Okay. But yeah, so I mean, but it is good. I think it is good to throw out fun ideas and maybe that idea sparks something else, right?
Any remaining questions? If not, let's speak a little more.
That's still also. I mean, for the magnet that we have already, yeah, we have.
He was not on.
Got a very specific thing.